Hello student and welcome for MD2 Machine Design 2 lecture series. Today we will discuss on the design of two-stage helical gearbox, or you can say two-stage helical gear pair. Just a minute, I will share my screen. Okay, for that we will take a simple example of design. The problem which is given over here. A two-stage complete helical gearbox is used to transmit power of 11.2 kilowatt from a motor rotating at 1500 rpm to a machine with approximate reduction ratio of 8. What we have to do, what in a problem we need to do, that is a select suitable material for pinion and gear for a second stage to satisfy strength and wear. Second, check the gears for dynamic load using berth velocity factor. And third, decide the constructional details for gear and pinion. And last one, make a neat and appropriate sketch of your gear design. Okay, so these points we need to analyze. Uh, in given, they explicitly said that you have to design second stage. Okay, you have to design second stage, and the reduction ratio for second stage is 8. Okay, sorry, total reduction ratio is 8 and we have to design for second stage. Okay, initially in figure you can see the appropriate layout for the gear arrangement. The enclosed type of system is used to avoid the wear. Then a motor with 1500 rpm is rotating, which is connected with the shaft number 1. The stage 1, there are two shafts, shaft number 1 and 2. So power is transmitted from shaft number 1 to shaft number 2 with the pinion P1 and P1 and with the gear G1, that is a first pinion and gear pair. In second stage, shaft number 2 transmits power to shaft number 3. Okay, then gear number 1 and pinion number 2 are rotating with the same speed. Okay, so that we have to consider. Then in stage number 2, after getting the reduction in power, we are supplying the output speed, that is that we have calculated over here, that is 530, sorry, 187 0.55 rpm towards the machine. Okay, that we have calculated. Let's see. First, note down the given data. Power 11.2 kilowatt, which is given. Speed of motor, that is 1500 rpm. Then transmission ratio is approximately 8. The speed reduction ratio for each stage, as they have mentioned, you have to design for second stage only. So that's why we need to identify the reduction ratio for each stage. Okay, so I is nothing but square root of I approximate, that is we get 2.8222, 2.828. So that much is the transmission ratio which can be used in stage number 1 as well as in stage number 2. Okay, so we need to find out the speeds, because input speed is 1500 rpm and we don't know what is the output speed, only we have a reduction ratio. So based on the transmission ratio for each stage, we can find out the speed, output speed. N1 divided by N2 is equal to I, that is 1500 divided by N2 is equal to 2.808, sorry, 2.828. Okay, so after calculating what we get, the speed of second number shaft is 530.41 rpm. That means the speed of gear number 1 and pinion number 2 would be 530.41 rpm. Now we need to find out the output speed of shaft number 3, that is the final output. So I is equal to N3 divided by N4. N3 is 530.41 and I is equal to 2.828. So N4 is equal to 187.55 RPM. So that much speed we need to provide to machine. Now first select the system and go for strength calculation. So initially, as I have mentioned in a figure, we are selecting the closed system to provide continuous lubrication and to control the abrasive, abrasive wear. Okay, and for that also we have considered 20-degree full depth involute to the profile system. Okay, now next one we need to calculate the minimum number of teeth on pinion. Okay, so to which we need to identify to avoid the interference. So Z minimum is equal to twice cos beta divided by sine square alpha. Now from PhD page number 8.1, uh, here the helix angle is not given, but from PhD page number 8.1 we can get the range. For helical gear it is in between 8 degree to 25 degree, and in case of herringbone gear it is 25 degree to 40 degree. Okay, as we are doing designing helical gear, so helix angle we can set in between 8 degree to 25 degree. Let's select helix angle is equal to 16 degree. Okay, it might be vary. So the minimum number of teeth are 17. Okay, by using transmission ratio you can calculate for the minimum number of teeth on gear. So 17 multiplied by 2.828, what we get? Approximate 48 number of tooth. So it is not divisible, both values haven't divisible by any common number, so we are not adding any hunting tooth in between. Okay, now next one, selecting the material. It is very important task because based on this material, the failure of gear or pinion will be decided. Okay, so as transmission ratio is less than 4, referring PhD page number 8.4, the material we have chosen for pinion is 40 Ni 2Cr 1Mo 28. And for in case of gear it is 15 Ni 2Cr 1Mo 15. Okay, so for that the sigma ut value you can find out from PhD page number 1.40. So value of sigma ut, that is ultimate tensile stress, is 1550 Newton per mm square, and the hardness HB is equal to 444. For similar we have noted down for gear. Okay, and both are case hardened. Now we need to find out the endurance limit strength, that is sigma dash 1. Okay, referring PhD page number 8.19. For alloy steel, sigma, that is the endurance limit stress for pinion, is equal to 0.35 sigma ut plus 1200. Okay, so that value is Newton. We need to convert it into kg per centimeter square. Okay, so the value of sigma ut is 1550 Newton per mm square. So we need to convert it into kg per cm square. That value will be 15,500. Okay, so put that value here. What we get? The endurance limit for pinion is 6625 kg per cm square. Using same equation, we can find out the endurance limit for gear. Okay, only we have to change the value of sigma ut. By changing the value of sigma ut, what we found that endurance limit for gear is 4840 kg per cm square. Now next we need to calculate the virtual number of teeth. Okay, so these virtual number teeth are equivalent to that of spur gear teeth. Okay, if it is compare with the spur gear, then this virtual number of teeth are equivalent. So we that's why we are always calculate this equivalent number of teeth, and this one is very useful to calculating the Lewis form factor. Okay, so virtual number of teeth for pinion, that is ZV1 is equal to Z1 divided by cos cube beta. So what we get, Z1 is equal to 19.13, and for gear ZV2 is equal to Z2 divided by cos cube by beta, that is 48 divided by cos cube into 16 degrees. So ZV is equal to 54. Now next stage is to calculate the Lewis form factor. From page number 8.50, Lewis form factor equation y v is equal to pi into bracket 1.154 minus 0.912 divided by ZV1. Okay, so putting all the values, what we get, the Lewis form factor in case of pinion is 0.334, and in case of gear it is 0.430. Okay, now we next step is to calculate the weaker element. Okay, so multiplication of endurance limit multiplied by Lewis form factor, you will get the exact strength. Okay, but in case of pinion it is 2212 kg per cm square, but in case of gear it is 2081.2 kg per centimeter square. So from these two value, what we get, the in this case the gear is weaker. Please note down, in this case the gear is weaker, so we have to start our design with design of gear. Okay, let's do it. Now find out the bending stresses by referring page number 8.18. We are assuming the power transmission only in a single direction. So sigma b, design sigma b is equal to 1.4 kbl divided by n into k rho and multiplied by endurance limit of gear. Okay, as we have already seen how we can find out these unknown parameters. For KBL, that is a life factor for bending, which we can find out from page number 8.20, table number 22. That is KBL is equal to 0.7, as the hardness is lesser than 700, lesser than the 350. N is the factor of safety, which we can find from PSG 8.19, table number 20, that is equal to 2. Okay, because we have considered here stainless steel material and the case hardened. Now K rho, that is a fillet stress concentration factor, which is we can find out from page number 8.19, table number 21, that K rho is equal to 1.2. So these are the repetitive tasks you always need to uh, know how we can find out it. So design sigma b is equal to 1976.3 kg per centimeter square, or you can say 197.6 Newton mm square. Next one, we need to find out the normal module. Referring page number 8.13a, Mn, which should be greater than or equal to 1.15 cos cube root of design torque moment and divided by Lewis form factor into design sigma b for gear psi m and z2. You can say z2 or zg. Okay, beta 16 degree Young's modulus, Lewis form factor, that is 0.431, psi m is equal to 14, and the bending stress is equal to 1976.3 kg per centimeter square. Only a known thing is torque. Okay, uh, MT design MT we can calculate is equal to MT into KDK from PhD page number 8.15. Now MT we can calculate by using power into 60 divided by 2 pi n. Okay, because we need to find out this for second stage. So power design power, we can say design power is equal to given power multiplied by service factor, that is 1.2. So design power is equal to 13.44 kilowatt. So MT is equal to 30.44 multiplied by 60 divided by 2 into pi into 187.55. Okay, you can use this equation, or referring PhD page number 8.15, there is another equation, you can refer that also. Okay, so we get power 684.311 Newton meter. So value of KD is equal to 1.5. As we are considering the unsymmetric and overhanging condition from page number 8.15. So value of MT is equal to 889.4 Newton per meter. You can convert this value in Newton mm also, so that you can get the final value of normal module in mm. Okay, so we convert that multiplied by 10 raised to 3. So putting all the values in equation, what we get, the normal module is equal to 2.76 mm. Okay, so referring the standard module from PhD page number 8.2, what we get, the nearest closest normal module is 3. Okay, you can go with the 3, or you can in uh, preliminary stage you can increase the module for 4 also. Okay, if it is not survived properly, or you can go with the 5 also. Let's initially we can just check whether it is survived or not. Okay, this model is in case of pinion, no sorry, in case of gear, but for pinion also we have calculating the value, that MT is equal to 97420 kilowatt divided by N. Okay, here we are putting the value of kilowatt and N. What we get, the design MT is 3205.41 kg centimeter. So here also, after calculating the value of Mn, we get is 2.5. Okay, but module 3 and 4 is failed in sigma u. When you're calculating the value, then you definitely find out that these are going to be failed. Okay, so to avoid the repeat calculations, we can directly select the normal module Mn is equal to 5 mm. Okay, so I suggest start with your design from module 5. Okay, so it can be sustained the both different loads. So first we will check for surface strength. Here we are checking for pinion as well as gear. Okay, for design surface strength, refer page number 8.16. Design sigma c is equal to cr into CHRC into KCL. Here CHRC will take 55 to 63 in between that. So we have selected that 60 because material is NiCr steel from PAG page number 8.16 table number 16. Okay, the life factor, that is KCl, from table number 17 PAG page number 8.17, as the strength is lesser than the 350 and the number of cycles are 2.5 into 10 raised to 7, the value of KCl is equal to 0.585. Okay, and the value of Cr is 310, as we know that, for steel, stainless steel, from PAG page number 8.16. So design sigma C is equal to 10,881 kgf per centimeter square. Now this we need to use to calculate. Here we need to check whether the module can be sustained or not. Okay, so referring PHG page number 8.13, checking for endurance surface strength or contact strength, then sigma induced, that is the exact stress induced inside the tooth, okay, that is equal to 0.7 I plus 1 divided by A into square root of I plus 1 divided by I into B into Young's modulus into design torque. So you can calculate the A, that is center distance, Mn divided by 2 of cos beta into Z1 plus Z2. So what we get, the A is equal to 16.9 centimeter. Width, that is 14 into Mi, Mn, that is 70 mm, that is 7 centimeter. Now putting all the values, what we get, the induced stress is 9642.66 kgf per centimeter square and the designed value is 10,881. So from both values what we seen, our design stress value, sigma C value, is greater than that of induced value. So our design is safe. Whatever the model we have selected, material we have selected, that is accepted. Now next one, we need to check these for different loading conditions, that is static loading, dynamic loading and wear loading. So dynamic loading we can calculating referring to different equations. Okay, so here we are referring PHG page number 8.51 and directly calculating the value of FD. FD is equal to FT into CV. FT is equal to horsepower multiplied by 75 divided by velocity. Velocity we can calculate pi dn by 60. So D is equal to Mn into G. So putting all the equation, what we get, Vm is equal to 2.45 second. Okay, this value is in meter per second. Meter per second. You need to change that unit, meter per second. Then birth velocity factor CV, which we can find out from PAG page number 8.51. CV is equal to 3 plus Vm divided by 3. Putting the value of Vm, what we get, CV is equal to 1.81. Okay, now we can able to calculate the value of FT. Okay, so FT is equal to 459.59 kgf, that is 4595.9 Newton. Now we have value of FT and CV. We can find out the dynamic load, that FD is equal to 8318.57 Newton. Okay, I have calculated in Newton. You can calculate in kg also, no issue. Now next we need to calculate the static load, that can be find out using sigma design bending stress into width into Lewis form factor into normal module. So putting all the values, what we get, the Fs value is 29,743.31 Newton. So when we compare the dynamic load and static load, as the static load is greater than the dynamic load, our first criteria is fulfilled, and hence for first condition our design is safe. Now second condition, Fw should be greater than the Fd. Okay, so let's see. First of all, referring PhD page number 8.51, you can calculate the value of wear load. The equation is B into dg q k divided by cos square beta. Okay, so where q can be calculated 2I divided by I plus 1, which is from page number 8.51. I value we have, so value of q is equal to 1.471. B already known, that is 7 centimeter or 70 mm. Dg, that is mn z2 divided by cos of beta. So diameter of a gear is equal to 88.42 mm. Value of k, that is sigma c square into sine of normal pressure angle divided by 1.4 into 1 upon E1 plus 1 upon E2. Here both materials are steel, so value of E1, E2 are 2.15 into 10 raised to 5. Okay, so putting all the values, what you get, K is equal to 2.69 Newton per mm square. Uh, Putting all the values in equation of Fw, what we get, Fw is equal to 26,613.25 Newton. As when we compare the value of Fw and Fd, value of Fw is greater, hence it satisfy the second criteria also. So both criteria are satisfied, hence our module selected and material selected are safe. Now next one, we need to find out the gear properties. So you can by using PhD 8 number 8.22, you can find out these different parameters for helix angle, normal pressure angle, normal module face width, PCD, tip diameter, root diameter, center distance, and tooth depth. You can calculate all the dimension in respect to the pinion as well as gear. Okay, so I hope you have understood how we can find out how we can design the gear in two different stages. Okay, design gear based on दोनों स्टेज को आप कंपेयर करो, जहाँ पे स्पीड कम है वही स्टेज आप डिजाइन करो, सो दैट क्या होता है कि वहाँ पे जहाँ पे स्पीड कम है वहाँ पे डेफिनेटली टॉर्क ज्यादा रहता है. ओके, एंड that stage only going for facing the huge torsional stresses. So if हम लोगों ने वो maximum stress पे एक बार डिजाइन कर लिया तो it can be sustained for normal stresses also. Okay, so always consider find out which stage should be having more torque transmission. Okay, okay, thank you. If have any query, you can contact me. Okay, I have shared the links for design in a description box. You can download it. Thank you very much.